Today we want to do even more derivatives. Remember the game. The game for derivatives is we learn some basic derivatives, some simple ones, and then we learn some rules for how to combine those simple ones into more complicated functions. As far as combinations go, we have rules for when the functions are combined by composition, that's the chain rule, by multiplication, that's the product rule, and by division, that's the quotient rule. So here we have a quick summary of each of those three. We've got to figure out what words, actually you have to figure out what words are going to work best for you to remember these rules. You don't have to memorize them, but you do have to remember them all the time because they are all always in effect. All we have to do now is add to the basic derivatives column of things that we remember. Eventually, we're going to learn to do this process backwards. So remember, there are two big questions in your Calc 1 class. What's the slope of the line tangent to a function at a given point? That is the derivative question. Then there's the other question. What is the area under a curve and above an integral? That is an integral question or an antiderivative question, which is just this process going backwards. This derivative process backwards is super messy and not as nice as derivatives. That's why I think we do derivatives first, even though the idea behind derivatives is more complicated than the idea behind area. All right, let's go over our basic derivatives because we're going to add to that today, and then we'll just do some practice. So in our basic derivatives, we've got the derivative of a power of x is nx to the n minus 1. The derivative of a variable raised to a constant, that's x to the n, is nx to the n minus 1. Switching this around and making an exponential function, a constant base with a variable exponent, the derivative of a to the x is a to the x times the natural log of a. The first rule goes along with what we know of the rate of change of a linear function. The rate of change of a linear function is constant. Linear is degree 1, constant is degree 0. So that tracks. The derivative of a quadratic function has a linear rate of change. Quadratic is degree 2, linear is degree 1. That tracks. We're one less than the original degree. That subtract 1 from the exponent. We know that the derivative of we know that the rate of change of an exponential function is proportional to the function, and apparently the constant proportionality is the natural log of the base of our exponential function. The more popular way we know the exponential function rule is with the chain rule and with the base of the natural logarithm. So our most popular use of the exponential function one is the derivative of e to the kx, and that's k e to the kx. Here we're using the chain rule and the fact that the natural log of e is equal to 1. Then to this we added sine, cosine, tangent, and secant. So the derivative of sine of kx is k cosine of kx. We usually summarize this by saying the derivative of sine is cosine and leave off the of x part. The derivative of cosine is negative sine. That's the way we summarize this one. The derivative of cosine is negative sine. These go together as a pair. The way we're pairing these up is that the sine and cosine, we start off with degree 1 trig functions, and we go to degree 1 trig functions. Sine of the first derivative is cosine of the first. Cosine of the first derivative is negative sine of the first. This is different with tangent and secant. The derivative of tangent of kx is secant square, k times the secant squared. So for tangent and secant derivatives, when we take the derivative, we go up 1 in power. So that's an interesting thing to note about these two. The same thing happens with cotangent and cosecant. With cotangent and cosecant, they also change signs. So the derivative of cotangent kx is negative k cosecant squared kx. The derivative of cosecant kx is k cosecant kx cotangent kx. But so far as your training in calculus goes, these are the 4 that we want to be aware of. Sine and cosine, secant and tangent. And you want to pair them up in your mind that way. You want to think cosine and sine are going together, tangent and secant are going together. The other 2 that you commonly study, cotangent and cosecant, we don't need those as much. The other 11, you don't have to worry about at all. You don't even know what they are. At this point in 2023, Cal students are like, oh, there are 6 trig functions. Meanwhile, crusty old mathematicians are like, oh, there's a lot more than that. But we have computers now, so we don't need any more than that. We just need to add to this list. One of the things that we want to notice about this particular process is there's not a lot of stuff that's deep that's going on. It's about reading and applying the rules. 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 Thousands of times. That's how you get better at this. Right now, you've done a handful of derivatives using product rule and chain rule. Not even a handful. Product rule we just started on Friday. So if you're like, oh, wow, this is so confusing, it's not. It's just confusing now. After you've done 10,000 problems by next week, you'll be fine. And it will be easy. So let's add some more base derivatives. What we want to notice, not only the rule that we need to know, the derivative of A is B. Not only that, but we want to think about what happens when we look at those derivatives. So the derivative of a polynomial drops down 1 degree. That's an important thing to note. More than just nx to the n minus 1, the derivative of polynomials drop down 1 degree. And radicals drop down, and we're going to call it degree, but drop down 1 degree. When the variable is the base and the exponent is constant, you subtract 1 from the exponent. When the base is constant and the variable is the exponent in an exponential function, you get a copy of your original function because the rate of change of an exponential function is proportional to the function. Sine and cosine, derivative of sine is cosine, derivative of cosine is negative sine. It starts with remembering those facts. You don't have to memorize it, you do have to remember it. But you want to notice that the derivative of sine is cosine. It starts off degree 1, and the derivative is degree 1. What's different about tangent and secant is that it starts off degree 1, we take the derivative, and now we've got degree 2. Different function like normal, but there's 2 of them. Derivative of tangent is secant squared. derivative of secant is secant tangent. It's like two of them. We want to look for when things change form when we're taking the derivative. Let's add some more base derivatives. This is an interesting one. The derivative of natural log of x is 1 over x. Derivative of natural log of x is 1 over x. Here's what's interesting here. We start off with this transcendental function, natural log of x. It's the inverse of e to the x. And the derivative of natural log of x is 1 over x. The derivative, when we find the derivative of this weird logarithmic function, we end up with a rational function. That's pretty weird. So the derivative of natural log of x is 1 over x. This is the inverse of e to the x. Speaking of inverses, the derivative of arctangent arctangent is inverse tangent. The derivative of the inverse tangent is 1 over 1 plus x squared. This has that same weird characteristic that the derivative of natural log has. We take some weird inverse function and we end up with the derivative. It's a rational function. So arctangent x is inverse tangent, or tangent inverse. This also might be written as tangent inverse of x. This is not tangent to the -1 x. It's not 1 over tangent. This is an abbreviation for tangent inverse. If you want to say tangent to the -1 power, you have to say cotangent. If you want to say tangent to the -2 power, you can write tangent to the -2 power. But if it's tangent to the -1, you want to write cotangent, unless you mean inverse tangent. Question? They are the same. It's just that tangent to the -1 is not tangent to the -1. When you see this with a tangent with this superscript of -1, you do not say tangent to the -1. I'll take off 1 billion points. I'm just kidding. It's 2 billion points. That's enough to put you all the way back in 3rd grade arithmetic. And you have to do it all over again. They made a whole Adam Sandler movie about this. I'm just kidding. So that's a particular notation, because usually when we want to refer to an inverse of a function, we use a -1 exponent. And some people are like, oh, dude, we use -1 exponent for reciprocal. And then the general consensus was like, oh, it'll be fine. And then the voiceover says, it wasn't fine. So then we're like, all right, what if we just called it something else, like arctangent? Leach is going to be all pedantic about this shit. Oh. So another inverse function that we should be familiar with, that's the theme for today, by the way. Derivatives of some of these inverses. Oops. Arctangent is so good, I wanted to do it twice, but let's do the other one. For inverse sine, or arc sine, the derivative is 1 over the square roots of 1 minus x squared. So arc sine, we could say arc sine, just like we spell it, or we could say inverse sine. And similarly, sometimes this is written as sine to the -1, but we don't say sine to the -1. So this is inverse sine. Natural log of x, of course, is inverse e to the x. And of course, there's a common one that we know for inverse secant. The most important thing is to realize inverse is the general word, reciprocal is specific to multiplication. A reciprocal is a multiplicative inverse. We are talking about the function inverse. Also, it's pretty easy to find. It's pretty easy to find if you forget. Just ask Dr. Google. Hey, Dr. Google, what are these? Notice that they have the 6 common ones, inverse trig functions. That's just excessive. Really, the most important ones are tangent, arctangent, and arcsine. Those you definitely have to have on hand. If you drop these absolute values off the arcsecant, no one will really notice. The rules for combinations are all still in play. The interesting thing that showed up here is that the derivative of arctangent, for example, the derivative of arctangent of x has a 1/1 plus x squared. The exponent went up. So that's a little bit weird. And it's also not just a power of x. It's 1/1 plus x squared. The main features that you want to look for tangent, sine, and secant, or sorry, arctangent, arcsine, and arcsecant. Arctangent has a 1 plus x squared or an x squared plus 1. Arcsine has a 1 minus x squared. And arcsecant has the other one, x squared minus 1. This is how we deal with quadratics. What we want to note is that arctangent, arcsine, and arcsecant have quadratics show up in their derivatives. And there are 3 ways those quadratics show up. X squared plus 1 or 1 plus x squared. That one's the same. Arcsine has a negative x squared positive constant. Arcsecant has positive x squared negative constant. So those are the things that you want to notice. Those are just noticeable because they come up later and they help us organize things in the future. So that's why I'm pointing it out now. Question? So arcsecant is the inverse of the secant function, not the reciprocal of the secant. In this case, this to the -1 exponent is indicating the inverse function, not the reciprocal. So the -1 exponent used this way is for inverse function and not reciprocal. So the -1 exponent when it's used in this way is used to indicate an inverse function, not a reciprocal. A reciprocal is a type of inverse function, specifically a multiplicative inverse. So a reciprocal is a multiplicative inverse. 5 times 1/5 is equal to 1. Because when we combine the reciprocal with the original under the operation multiplication, we end up with the multiplicative identity. So when we write sine of, let's say, pi over 6 is equal to 1/2, we are talking about the function that we apply to 1/2 to end up back at pi over 6. So the inverse, let's see, oh, sine was in green, so we'd say sine inverse of 1/2 is pi over 6. We're talking about the inverse function. But because we use the -1 exponent to indicate the inverse and also to indicate a reciprocal, just the specific multiplicative inverse, we're like, oh, that's kind of shitty on our part. That's where we're like, oh, this might cause problems. And then everybody's like, oh, nah, it'll be fine. And it wasn't fine. So then we're like, oh, what if we just said, instead of sine inverse, let's replace this with arc sine. Then we're only left with pi being the ratio of the circumference to the diameter, when maybe it should have been the ratio of the circumference to the radius, since the radius is more of a defining characteristic of a circle. But then they're like, oh, but then Pi Day would not be in March, where we could do it in school. Pi Day would be at the end of June, and everybody's out of school, so it wouldn't be fun. It's like, oh, I don't know why you're thinking about what Americans are going to be doing 2,000 years from now, but we should make pi 6.28, not 3.14. I missed that meeting back then. So I had like a full list of arguments. Like, oh, look, there's trig coming up, and it's much more convenient if one circle is just one thing. Like, let's use the radius. Say pi is the ratio of the circumference to the radius, not the diameter. It's not like you use the diameter to make the circle anyway. You take the diameter, you cut it in half, and then you build the circle, because you need the fucking radius. But anyway, they were pretty dumb back then. I mean, they didn't even have algebra. Dumbasses. Just kidding. All right. So we just need to learn these rules and incorporate them. Notice the weird things that happen when we're finding derivatives now. Everything was pretty predictable. We related it all back to rates of change. But we need to practice with the rules. So we would need to be able to do things like find the derivative with respect to x of arctangent of 5x cubed. Now, A perfectly valid question is like, oh, why would we need to find the derivative of arctangent of 5x cubed? And the answer, of course, is like, shut up, you. We're going to practice this stuff. Quiet, you. We're training here. My response, my typical response is like, oh, lateral raises. Lateral raises is the answer. So everybody know what a lateral raise is? So when you have like something heavy in your hands and you like hold your arm out like this, right? But the trainer's like, oh, do some lateral raises. And they're going, all right, I'm going to take off like a bird, right? No one ever is like, oh, when am I ever going to pick something up this way? That's not how you pick stuff up. But anyway, but math is like, oh, let's do some lateral raises. Like, oh, why am I have to do this? When am I ever going to have to do this? And I'm like, oh, well, not good. You're not, because good news. You marry a billionaire, so you don't have to work ever again in the rest of your life. So just get to that point and you'll be fine. We just got to practice. What's the derivative of arctangent of something? The derivative of arctangent of something is 1 over 1 plus that thing squared. So the derivative of arctangent of a thing is 1 over 1 plus that thing squared. That's the form. That's the thing that we fill in. But then we got to use the chain rule, right? So the derivative of arctangent of 5x cubed is 1 over 1 plus 5x cubed all squared. Then we have to multiply by the derivative of the inside, which is 15x squared. Never forget, you have to turn to face the strange change rule. This is a good way to write it to show me that you have done the thing. But this is not how we would want to write our answer with our fractions all split up like this. It's like really bad to have fractions that are being multiplied together, because then it looks like you're trying to make a mixed number out of it, which is actually plus and not times. So I'll put the 15x squared up on the top. And in the denominator, I'll write 1 plus, let's go crazy, 25x to the 6th. That way we can hide what we did to get this answer. And since we're practicing, we just start doing some silly shit. Now it's arctangent to the 4. So I've got the 5x to the 3rd. I've got the 4th power of arctangent of 5x to the 3rd. So that shows me that we're going to have 3 things. So we're going to have to do 2 chain rules. You just have to read what's on the outside. It's the 4th power of arctangent of 5x to the 3rd. So the first thing that we find the derivative of for the chain rule is the 4th power. The derivative of something to the 4th power is 4 times that thing to the 3rd power. And it's of arctangent of 5x to the 3rd. The derivative of something to the 4th power is 4 that thing to the 3rd power times the derivative of that thing. The derivative of arctangent of 5x to the 3rd. The derivative of arctangent is 1 over 1 plus that thing squared. And in this case, that thing is a 5x cubed. Then the chain rule says multiply by the derivative of that thing, which is the 15x squared. Now, if you're looking at this function and say, this looks awful, of course it looks awful. Look at the function we started with. What a dumb function to start with. But as a reading exercise, that's what this is for. Lateral raises. Walking lunges is another one. That's not how you walk around. So why do I have to do these walking lunges? That is not how I walk. See, I walk normally like this. I'm not trying to do some weird combination of exercise and Chuck Berry or something. No one walks like that. Clearly, we would want to clean this up. So I got a 15x squared and times 4. So I'm going to have a 60x squared arctangent cubed of 5x cubed. And in the denominator, well, we might as well clean that up since we're on a cleaning up business here. It's a 1 plus 25x squared, or x to the 6th. Reading exercise. What's going on in this function? When you see some messed up function like this and you're trying to figure out what's going on in this function, one of the things that's going to occur to you is like, well, when am I ever going to encounter this function? So I don't know, you just did. Now I've got x to the 4th times arctangent of 5x cubed. What rule are we going to have in play here? A chain rule and a product rule. What's going to be our primary rule that we're going to fit things into? Is it primarily a chain rule or primarily a product rule? So notice you've got this x to the 4th and then the arctangent of 5x to the 3rd, and these things are being multiplied. So this is primarily going to be a product rule. You can say our first is x to the 4th, and our second function is arctangent of 5x to the 3rd. So the derivative of the first is 4x cubed. The derivative of the second, the derivative of arctangent of a thing is 1 over 1 plus that thing squared times the derivative of that thing. Product rule says take the derivative of the first times the second plus the first times the derivative of the second. I'll just put the 4th up here. How's everybody okay? Anyone want to cancel those x to the sixths? He said, setting a trap for his students. So cool. Now, we're not going to cancel the x to the sixth because there is no x to the sixth factor in the denominator. As written, there is an x to the sixth factor. We can cancel those six, the x to the sixth, but this one is going to come out badly. You can cancel x to the sixth as long as you do it out of all three of the terms. Notice that this x to the sixth down here with the 25, it's not being multiplied by all the stuff down here. It's being multiplied by the 25, but not the 1. Now, we can, if we wanted for some reason to have a constant numerator, like really badly, then we could. We could be like all 15 and then make this 25. But then that dividing by x to the 6 would show up there. Don't forget your distributive property. At this point in your mathematical career, for the most part, when we ask the question, is it factorable? The answer is like, oh, yeah, as long as you're okay with things not being integers all the time. But not in any kind of traditional sense. Does that make sense? Incidentally, you don't want to just cancel those x to the 6. You might think, oh, these are weird rules of algebra. There are no weird rules of algebra. This is just the numbers telling us what they do. We can't cancel those x to the 6 because that's not how numbers work. That's it. Whenever there's something you can't do in algebra, it's because numbers don't work that way. If I take, let's say, 75 and divide it by 5, I can't just cancel these 5s. Because the 5, when I write 75, that 5 is included by addition. Right? That 5 is included by addition. So if we had set, when we split it into a polynomial, and then if instead of a 70, it's just like a 7x. You can't do it here because that's not how numbers work. Not because of rules or any shit like that. That's just not how numbers work. Right? Make sense? How's everybody okay? Sometimes we write things in a kind of a fucked up way. It's kind of messed up. Like the number 2.5. This is, or let's go 2 3/4. This is really annoying. Because normally when we take two numbers and jam them together, what are we doing with those numbers? We're multiplying, right? So if I like put 5x, that means 5 times x. But if I take a whole number and write it, jam it up next to a fraction, now what operation we talk about? Now it's fucking addition. God damn it, you guys. Not you guys. The guys that came up with this shit. It's like, wait, let's try 2 3/4. Should we maybe indicate that we're saying and in the middle? Trying to indicate that it's plus? It's like, nah, it'll be fine. It wasn't fine. You know what I mean? How would you take 2 3/4, 2 3/4, and turn it into an improper fraction? What would you do? Anyone know this one? Where you do 2 times 4, and then plus 3. So you do 2 times 4 plus 3 over 4. Right. What are you doing when you do that? We're getting a common denominator. You're just trying to make them the same. The reason that we have this shortcut is that the denominator of the 2 is a 1. And so to make that denominator the same, all we have to do is multiply by 4. And then you get to algebra. Get later on in algebra, you're like, well, I've got this. And you're like, well, that's awesome. What is 2 plus 3 over x minus 4? And I'm like, oh, well, I don't know. It's like, oh, fuck, it's the same thing. 2 plus 3 in the denominator is x minus 4. 2 times x minus 4 plus 3 over x minus 4. Oh. Algebra. Most of algebra could be like, oh, hey, remember arithmetic? Just do that. But doing that would require a proper basis in arithmetic, which a lot of people don't have. Because it's not practical to do. You know what I mean? Anyway. Learn your new bit today on the list of things. TLDR. 4 new derivatives. Really only 3. This arc-secant one, I mean, you're just going to be extra if you have that one. If you need to go that extra mile, after people list off those first 3, it'll be like a derivative of arc-secant is 1 over the absolute value of x times the square root of x squared minus 1. Now, if you learn arc-secant in this class, that's how snotty you have to be when you say it. You have to be like that. More. Oh, I know more. Then if you really want to know more, learn arc cosine and arc cosecant and arc cotangent, where you kind of have to just multiply by -1. And then you'll be like extra fast. All right, that's it for today. 3 new that you really have to know. More practice with your basic combination rules, chain rule, product rule, quotient rule. That's it for today. I will see you all on tomorrow. Have a good day. And thanks for playing.